Hi, welcome to the second video of the series where we're going to define three crucial norms: the Frobenius norm, the operator norm, and the nuclear norm. I'm going to go through them really slowly and they'll take a while to absorb. And I suggest that time be spent thinking about why these are norms and, like associating them with quantities that you already know from vector spaces. Now let's look at the first one. The first one is the Frobenius norm. The best way to think about the Frobenius norm is as the matrix analog for the Euclidean norm. So the closest match is for vectors. We have this is the dot product, or the square root of the dot product, which is written as the sum of xi squared from I is equal to 1 to n, right? So what we have for matrices is that the Frobenius norm is defined again as the square root of a dot a. Now this dot product was defined in the previous set of tutorials as the trace of a transpose a. So this is the square root of the trace of a transpose a. Now if a is just u d v transpose, then a transpose is v d u transpose. So remember that d is diagonal, so d transpose is exactly d. And in that case, a transpose a is just v d u transpose u d v transpose. Now remember that u transpose u is the identity for the SVD, and so we just get d times d. Since this is a square matrix, diagonal matrix, we can just write that as d squared. So we just get trace of vd squared v transpose. And now we apply trace rotation. If you don't remember what trace rotation is, it says that trace of AB is equal to the trace of BA. So we can use trace rotation to send this V to the other side, right? So we'll get a V here and this V will disappear. And now V transpose V is the identity according to the SVD. And so we just get square root of trace of D squared. Great, so how does that help us? So firstly, this part was just by the definition and this part was using the SVD. So we can get the Frobenius norm in two different ways. Either we can take, what if you expand out trace of A transpose A, you just get the sum of I is equal to 1 to m, j is equal to 1 to n, aij squared. So this looks a lot like a summing over the squares of all the entries of the matrix, right? But it's also gotten by the sum of I equal to 1 to r of di squared, where these are the singular values. So this is actually like the L2 norm of d, where d is basically the diagonal of the capital D from the singular value decomposition, right? So it's interesting that you can either get it in terms of the entries of the matrix or in terms of the singular values. Now, just note that this is actually a valid norm. We're calling it the Frobenius norm, but it is an actual valid norm in terms of the properties of norms that we saw from the earlier set of tutorials. Remember that it is derived from an underlying dot product. So it is defined in terms of this dot product. And we know that any norm that comes from an associated dot product is a valid norm, as seen in the previous set of tutorials. Now let's move on to the next norm, which is called the operator or the spectral norm. You'll hear people using both terms, so it's good to know both of those terms. Now the operator norm is the largest singular value of A. Now again, if D was written in such a way that it had non-increasing diagonal entries, then we're just looking at the first of those diagonal entries, and that's the largest singular value of A. Now it's important to remember that all the singular values are always positive. So singular values are always greater than or equal to 0. So the largest singular value of A is also always positive. And one can think about it in a different way. One can think about it as the infinity norm of D, where D is just the diagonal of capital D. The infinity norm is the maximum element of D, and that's exactly the operator norm. Again, this is actually a valid norm, and one can go back and try to check this property. But this is a valid norm in the sense that it satisfies those 4 properties we needed of a norm. Another equivalent way to describe the largest singular value is to look at A transpose A. So this is A transpose A. Now A transpose A is V D squared V transpose, and actually similarly AA transpose is U D squared U transpose. Now both of these matrices are actually positive semi-definite, and VD square V transpose is the eigenvalue decomposition of A transpose A, and UD square U transpose is the eigenvalue decomposition of AA transpose. If you're unfamiliar with what the eigenvalue decomposition is, I suggest looking up some other linear algebra tutorials. And now D squared contains the eigenvalues of this matrix, and if I take the largest eigenvalue, that's going to be D1 squared, and if I take the square root of that, it's just D1, right? So that's exactly what we wanted. So another way to calculate the largest singular value is to calculate the largest eigenvalue of A transpose A or AA transpose and take the square root. And this is basically the idea that we come across in PCA, where we look at the covariance matrix and the largest eigenvalue of the covariance matrix, and instead of that one could just do the SVD of the original data matrix. And if you don't know what I'm talking about, that's fine, you'll come across it at a future point. Lastly, let's discuss the nuclear or trace norm. Now the nuclear norm, it's often given by a star. It's the sum of all the singular values of A. So one can think about it as the one norm of D. Okay, so maybe pen failure right now, but you should think of that as the number 1, right? So this is the one norm of D. It's the sum of all the DIs. Now since the DIs are positive, I don't need to take their absolute values. Now again, this is a valid norm, and it satisfies all the properties of a norm. You shouldn't just take my word for it. You should go back to the previous set of tutorials and look at the properties that a norm needs to satisfy, and convince yourself that the nuclear norm, that is the sum of the singular values, actually does satisfy all those properties. So these 3 norms in some sense capture the strength of the matrix. Like just like the 2 norm, the infinity norm, and the 1 norm capture in some sense the 2 norm captures the length of a vector, the infinity norm captures the the largest box in which you can fit the vector, and so on. And in a similar sense, the Frobenius norm, operator norm, and nuclear norm capture the size of the matrix, if you want, the amount of energy in the matrix in some sense. A matrix with a smaller nuclear or operator or Frobenius norm is going to have much smaller entries in it. All the singular values are all small, and that basically means that all the entries of the matrix are also going to be small. And similarly, if any matrix has a very large singular value, this is going to be reflected in the size of the entries of the matrix, and some of the entries of the matrix are going to be really large. That's all I want to say for the moment about these 3 norms. It's not really possible to define the operator and the trace norm without knowing the SVD, the definition of the SVD, and so you can clearly see the relation to SVDs. But in the next video, we'll see that the SVD plays an even more crucial, these norms play a crucial role in understanding the SVD, and that's coming up in the 3rd video.